Lightning McQueen races on a racetrack curve of radius r. The racetrack is banked at an angle theta. The coefficient of static friction between the tires and the roadway is mu s. What minimum speed is required so that Lightning McQueen does not slide down the banking? I'm going to draw a 3D picture and a 2D picture of what's going on. The 3D view looks like this.
You actually got an image of Lightning McQueen.
Yes. And now let me draw the 2D view, and it's banked at an angle theta. A bank angle is the tilt of the roadway in a curve. So it's measured between the horizontal and the surface of the track. So this angle right here. And what's the point of a bank angle? Why not just have a flat road? The bank angle is used to help the vehicles turn safely at higher speeds. Let's label the forces on Lightning McQueen in the 2D view. So we have weight, we have mg going downward, we have the normal force, and we have static friction between the tires and the roadway. So here's the weird part. This static friction actually points up the racetrack like this. If Lightning McQueen is going too slow, then he's going to start to slide down the road. So static friction is keeping Lightning McQueen from sliding down the road. What I also find weird about this problem is that it's static friction. Like Lightning McQueen is moving. Shouldn't it be kinetic friction? It's static friction because if you have a car rolling normally, the point of the tire in contact with the road is instantaneously at rest relative to the road. So the tire isn't sliding across the road. So since it's not sliding, it's not kinetic friction, it's static friction involved. So the static friction is what allows the tires to push against the road and change the car's motion without slipping. So that's why it's static friction. That's why it's up the road. So back to what I was saying with the bank angle, it's used to help the vehicles turn safely at higher speeds because now there's a component of the normal force that's pointing towards the center of the curve. So it reduces the reliance on friction to prevent sliding. So basically, the banking helps the car stay on the curve by partially leaning into the turn. Remember, this is a circular racetrack. So A rad in this 2D view is going to be pointing horizontally to the right. So this is A rad right here.
Totally radical, dude.
Yes. Ka-chow. Try not to cringe. Try so hard not to cringe. Okay. So we want the minimum speed required for Lightning McQueen to not slide down the banking. We need to find A rad because A rad is speed squared over R. And to find A rad, we need to analyze the forces. So we have to use Newton's second law. And what coordinate system is going to make our lives easier? Are we going to do parallel and perpendicular to the road? Or are we going to do just the normal horizontal and vertical X and Y axes?
Perhaps the parallel and perpendicular directions would suffice because Fs and N are already in that system.
It's a good idea to align one of your axes in your coordinate system with the acceleration vector because it's not very fun to have A in this direction and A in the other direction. It's good to just have one A. So, kind of surprisingly, it's better to use the standard X and Y coordinate system for this problem. And X is basically the radial direction because remember, this is the circle and X is pointing towards the center of the circle. All right. So let's find A rad, and then from there we can find V. A rad is in the X direction. So let's look at the sum of the forces in the X direction. Let's break the normal force and the static friction force up into its components. The net force in the x direction is just nx minus fsx. And a in the x direction, that's just a rad. Okay, so again, we want a rad to find v because a rad is v squared over r, but we don't know what nx is and we don't know what fsx is. We need to relate that to what we do know, which is theta. So which one's going to be n sine theta and which one's going to be n cosine theta? We're looking at nx right now. So is nx n cosine theta or n sine theta? Let's go back to geometry and see which angle is theta. I'm going to draw two parallel vertical lines cut by this line here, this transversal. We're looking at this triangle and this triangle. So they both have 90 degrees here. And this angle right here is 90 minus theta because this is theta and this angle and this angle have to add up to 90 degrees. So that means this angle right here is theta. Since we know this is theta, this also has to be theta because they're alternate interior angles. Let's look at this triangle right here. Which angle is theta there? If this is theta, this is 90 minus theta, right? And this is 90 degrees. So this has to be theta because we have theta plus 90 degrees plus 90 minus theta, and you get 180 degrees. So nx is opposite theta, so it's n sine theta. And fsx is adjacent to theta, so it's fs cosine theta. And we're trying to find the minimum speed, so I'm going to write a rad as v squared over r. So the right-hand side is m v squared over r. We have theta, we have r, we want to find v. And we don't know m, we don't know f sub s, and we don't know n. Let's tackle f sub s because there's a formula for that, right? F sub s, recall, is mu s times n. That's the maximum static friction force. We're trying to find the minimum speed. So to find the minimum speed that prevents sliding down, the static friction will be at its maximum value. So this is really Fs max, and it's mu s times n.
And we're given mu s, aren't we?
Yep, mu s is given right here. So now we need to find n. To find n, let's use Newton's second law in the y direction. So the net force in the y direction equals m times a in the y direction. So the net force in the y direction is ny plus fsy. I'm adding them because they're both upward, minus mg because mg is downward. And ay, that's just 0 because the only acceleration is a rad, and it's 100% in the x direction. So this equals 0. I mean, that's why I did this coordinate system, so I don't have to have a rad one direction, a rad other direction. I can just say, oh, then this direction is 0. Okay, so ny is n cosine theta because ny is adjacent to this angle. Fsy is fs sine theta because it's opposite theta. And we just have minus mg equals 0. So we're trying to find n. Remember the maximum static friction force is mu s times n. So I'll substitute that. And to find n, I'm going to factor out the n from the first two terms, and I'm going to add mg to both sides. So you're going to get this. Okay, and to isolate n, now I just have to divide both sides by cosine theta plus mu s sine theta. Okay, so you get n equals mg divided by the quantity cosine theta plus mu s sine theta. So we know theta, we know mu s, we know g. The only thing we don't know is m, but we'll worry about that in this equation. So I can substitute n now. Let me just factor out the n. So we just have one n to worry about. And now I can substitute this for n. So you'll get this. So the great thing is that m cancels out, which
So
means
we were never even going to use it at all.
exactly. So it doesn't matter. We don't have to worry about it anymore. And we're trying to find the minimum speed v. So
Just apply R and square root that thing.
exactly, I'm going to multiply both sides by r and take the square root. So you'll get this. We're basically done. You can technically box this answer right now, but you can clean it up a little bit. What I'm going to do is I'm going to factor out cosine theta from the numerator and denominator. So you'll get this. So notice how when you factor out the cosine, you have sine over cosine, which is tangent. So these cosines will cancel. So that's the minimum speed Lightning McQueen has to travel so he doesn't slide down the banking. So it's the square root of GR times tangent theta minus mu s divided by 1 plus mu s tangent theta. So this is in terms of everything that was given in the problem because we're given theta, mu s, and r. That is it for today. I hope you guys enjoyed, and I'll see you guys very soon. Have a ka-chow-tastic day.
Oh dear. Yeah, have a day.